Well, hello again. Hopefully everybody's doing okay. Today in statistics, we're going to start looking at chapter 8 in your book. And to get started with that, you notice I put a picture here of some stuff that's been in the news quite recently. We have President Trump here standing next to Dr. Anthony Fauci, and those two people have argued quite a bit recently about just what is going on or what might be done to solve the problems with coronavirus. You can see a headline here that shows one of the disputes that President Trump and Dr. Fauci had with one another. It talks about Trump touting a drug called hydroxychloroquine. This is a drug that's been used in the past to treat malaria and lupus, and there have been some rumors that it could be a treatment for COVID-19. Now, President Trump talked about it as if it was a cure for the coronavirus disease. Dr. Fauci, on the other hand, walked back those comments and said that this is not something that we can say is going to be a cure. The difference between what Dr. Fauci and President Trump say really boils down to their understanding of how statistics and science in general works. And Dr. Fauci will tell you that we can't say that this drug is a cure because it hasn't been tested. There have been a couple of small situations where it's been shown that it might have some benefit, but a couple of situations doesn't prove anything in medicine or elsewhere in science. To do that, you need to do what's called a hypothesis test, and that's exactly what we're going to be learning how to do as we go through Chapter 8. Hopefully you remember from earlier in the semester that the word significant, I told you, was the single most important word you were going to learn in statistics, and what it meant was that you had a result that didn't happen by chance. Well, it turns out that one of the most common questions that we ask in statistics is whether results are significant or not. Basically, you're asking, if you did this again, would you probably get the same result, or did it just happen by chance? To see if something is significant, we do what's called a hypothesis test. Hypothesis is basically just a scientific word for an idea, and what we're trying to do is see what idea is going to end up actually being true. In statistics, we look at two different hypotheses, and essentially what those say are this is significant or it's not significant. We need to figure out which of those is going to be happening. You can never prove something 100% in statistics. So what we do is we say that a result's going to be significant if there's a very, very, very low probability that it just happened by chance. Now, just how low that probability is depends on what kind of a problem you're doing. In a place like medicine, like if you're trying to show that a new drug actually would treat COVID-19, we would want that probability to be really, really low. You don't want it to just happen fairly frequently by chance. From your point of view, doing a hypothesis test is basically going to be a lot like those estimation problems you just got done doing. You're going to punch some numbers in your calculator and see what the results end up being. Before we get into doing that, though, I want to look at the idea of what hypotheses actually are. When we do a test for significance, there's always two possible outcomes that we look at. The official names for those are the alternative hypothesis and the null hypothesis. Most of the time, those are abbreviated with the symbols H1 and H0. 1 and 0, some people know from like electronics, are just a symbol for on and off. And basically, it's like we're turning significance on or we're turning it off. Alternative hypothesis is good, null hypothesis is bad. Basically, the alternative hypothesis just says that a result is significant. Now, one of the things that you're going to be asked to do in problems is to look at a problem and come up with what are the alternative and the null hypotheses. The easiest way to do the alternative hypothesis is just to read through the problem, look at the question it asks, which is usually the very last part of the problem. Basically, you copy the question, but instead of writing it as a question, you turn it into a statement. I'll show you exactly how that works here in just a minute. The null hypothesis, null, by the way, is just the British word for nothing. That's why we have H0 as the symbol. The null hypothesis says that you don't have a significant result. And the easy way to do that is to take the alternative hypothesis that you just found and just throw the word not in there. So let's look at a couple of examples. First one here, I shortened up from what you might see if you were like doing a problem in the book. It starts off by saying a 2017 poll asked people for their opinion on President Trump and President Obama. And of course, the book would give you all the background on how they did the survey and what exactly were the numbers that they got. But at the end of it, it would ask a question like, was Trump's approval rating significantly lower than Obama's? Well, here's the two hypotheses. All I do for the alternative hypothesis is I just look at that last sentence. What it said in the problem is, was Trump's approval rating significantly lower than Obama's? And I just turn that around and make it a statement. Trump's approval rating was significantly lower than Obama's. Now, I don't know if that's true or not, but it's my alternative hypothesis. It's what we're looking at for this problem. The null hypothesis, I just take what I just wrote there and I toss in the word not. Trump's approval rating was not significantly lower than Obama's. So again, I basically just copy the question, but make it a sentence. And then I throw in not. Something that's kind of important here is that the null hypothesis, which here is that Trump's approval rating was not lower than Obama's, it doesn't mean that it was higher. Not lower would mean that it's not less than, and that means it could either be greater than or equal to. Most of the time when you get a result that's not significant, it's really that equal to that you have. It would mean that they're about the same. And in fact, in the real world, both of those presidents were not terribly popular in the great scheme of things, and so yeah, they probably were about the same. Well, here's another example. It says, Iowa Lakes reports that its average class size is 16. I'll tell you, I totally made up that number, but we're going to use it for this problem. A sample of the classes at the Algona Center is taken. Do classes at the Algona Center average significantly less than 16 students? So again, what I want to do is look at that question, and when I come up with the alternative hypothesis, we're just going to turn it around and make it a statement. When I do the null hypothesis, we'll toss in not. And that's why in this problem, our alternative hypothesis would be that the Algona Center's classes average less than 16 students. The null hypothesis would say they don't average less than 16 students. Again, it's always one or the other. And if it was not less, that would not necessarily mean it's more. It means it's probably about the same as that 16. Now, I've found, having taught this for years, that for most students, the easiest way to come up with hypotheses is to do exactly what I just said, which is look at the problem, turn the question into a statement, and then toss in not. In the book, they tend to write things so that they look like math. You don't have to do that, but I mention this for a couple of reasons. One of them is sometimes there'll be people that look up the answers in the back and they don't always realize that they're saying the same thing just in a different way. The other one is some of you may end up in a different statistics class at some point, And it's always good to have an idea when you see something new what it's talking about. So the book would write this as mu is greater than 16 and mu is less than or equal to 16. Mu just means the average for the whole population. So this would be saying like the average of all the classes in Algona is greater than 16 students. The other one, the null hypothesis, would say it's less than or equal to 16 students. Again, I'm fine with you just writing that in words, but the symbols are okay too. It's fine to write it either way. I'm going to take a quick look at another couple of examples of alternative hypothesis and null hypothesis. Here's one where they're just showing you how a difference might work. One of them says the application of biofertilizer X increases plant growth. And the null hypothesis says that application of that fertilizer does not increase plant growth. And again, you got to think about, yeah, it either is going to happen or it's not going to happen. Yes is always alternative, null is always no, it isn't happening. I'm going to look at another couple of examples of hypotheses. Here's one where they're talking about applying fertilizer, and the alternative hypothesis might be that this fertilizer is going to increase plant growth. The null hypothesis would be that it isn't going to increase plant growth. Again, alternative is always there is a difference. Null hypothesis is there's not. You can tell I just did kind of a quick image search for a bunch of things. Here's some other examples of things that might be null hypotheses. One of them says cats show no preference for food based on shape. The alternative hypothesis here would be that cats do express a preference for food based on shape. In the middle it says plant growth is not affected by light color. Well, the alternative would be it is affected by light color. And the last one there, age has no effect on musical ability. That's the null hypothesis. The alternative would be that age does have an effect on musical ability. So again, if there is some difference, that's the alternative, the H1. If there's not, that's the null hypothesis, H0. The whole idea of why a hypothesis test works is that the alternative hypothesis and the null hypothesis are always opposites of each other. And one or the other of them has to be true. Either this is a significant difference or it's not a significant difference, and what we've got to figure out is which one's happening. The official way that a hypothesis test works is that we show that the null hypothesis can't possibly be true. And so if it can't be true, the only thing that could happen is the alternative hypothesis, which is a significant result. It's almost like you're taking the null hypothesis and you're putting it on trial. And you show that it can't have committed the crime, so you throw it out. And then what's left is that alternative hypothesis. Statisticians do call the idea of getting a significant result rejecting the null hypothesis. That's again not something that you really have to know for this class, but if you do run into another statistics class down the road, there's a real good chance you'll hear that term. And if you do reject the null hypothesis, all that means is you've got a significant result. There's an important term that comes up with hypothesis tests that's called the level of significance. To stand for the level of significance, we use a Greek variable called alpha. Alpha is just the first letter of the Greek alphabet, and we use the lowercase one for level of significance. It looks almost like a little fish symbol when you write it out. The level of significance is how often we're willing to accept that a result's significant when it actually just happened by chance. We say that it's significant, but really it wasn't. And alpha is the amount of time that we're willing to let that happen. So it's the probability that we said this result's significant, but actually it just happened by chance. Basically, it's how willing we are to be wrong when we say a result's significant. It's kind of like the opposite of the level of confidence that you did with estimation. Confidence was like what percent of the time you were going to be right in your estimate. The level of significance is how often we're willing to be wrong. And since it's how often we're going to be wrong, we want that level of significance to be a low number. You don't want to be wrong like 80% of the time, or really even 20% of the time. Most of the time, they're going to give you a level of significance in the problems that you have to do, and the numbers that typically get used are 10%, 5%, and 1%. They're very often given to you as a percentage, but when we treat them in problems, we always think of them as decimals. So like 10% is going to be 0.10, 5% 0.05, and 1% would be 0.01. The more important of the research that you're doing, the lower that number should be. In medicine, 1% is about the biggest level of significance they'll use, and in fact, a lot of times in medicine, they might even go down to 0.001, where it's like 1/10 of 1%. It's important research. You want that to be a low number. On the other hand, in places like business and education, they'll sometimes use 10%, and that's because if you're wrong in a place like business or education, really all it does is cost you some money. It's not like somebody's going to die because you were wrong. So what we need to figure out today is exactly what happens when we do a hypothesis test. The theory behind it says that we're going to take the result we got from when we did a sample, and we compare that with every possible sample that could conceivably have been taken. That's called the sampling distribution. And basically, we want to know if you just randomly pick samples all day, would you be likely to get the results we got or not? What we hope happens is that our result is clear out in the tail of the normal curve in an area where things don't happen very often. If it's clear out at the right or clear out at the left, that's when we're going to say that we have a significant result. If we got a result that was in that big bulge in the middle, that can happen a lot, and that would not be a significant result. It could pretty easily happen by chance. So we're going to say that a result is significant if it's big enough that it's out in the tail of the normal curve. It's beyond all of those results that could have happened by chance just due to our sampling error. And significance in the tail where it doesn't happen very often. And that tail could either be the right side, like I have the arrow on in the top, or it could be the left-hand tail as well, where it doesn't happen very often over there. There are actually a whole bunch of ways that you can do hypothesis tests. We're going to do what should be the easiest possible way, and that's partly because we have to learn how to do this online as opposed to having a lot of opportunity to do it up close and personal. What we're going to learn is what's called the p-value hypothesis testing method. The good news about that is not only is it the easiest way, but it's also the most common way that people do hypothesis testing these days. So p-value is the key to what we're doing. And basically what's going to happen is we're going to calculate the actual probability that something happened by chance. That's what the p-value is. And we're going to see if that's less than that level of significance, the error that we said we were willing to accept. This is mostly going to be done on your calculator, and it basically boils down to 3 simple steps. The first step is making sure that you know the level of significance. Remember, that was the amount of the time that we were willing to accept that we might be wrong. Now, when you're doing a problem that's in the book or on a worksheet or on a test, that number is always going to be given to you. Just like when you were doing the estimation problems in the last chapter, they always gave you the level of confidence. It's going to be given in the problem, and you just need to sort through and make sure you know what that number is. In the real world, they don't give you those numbers. What you need to do if you were like doing statistics for a job is you need to think, how important is this research that I'm doing? And the more important it is, the lower you want that alpha, that level of significance. Once you know the level of significance, the next step is to calculate the p-value. In this class, what we're going to do is use your calculator, your TI-83 or 84. We're going to go into that Stat Tests menu, just like you did in the last chapter, but we're going to go to other places in that menu, and we're going to be able to just enter some numbers, find out what that is. If you didn't have a calculator, honestly, in the real world, what you would probably do is calculate that through a spreadsheet or through some other piece of software. What's built into the calculator and into various software programs is just a formula, and back in the Stone Ages, you would have cranked that out to find out what the p-value was instead. Remember, what you're finding with the p-value is the actual probability you're wrong, the actual probability something happened by chance. And the final step is just to compare the two numbers. P is the actual probability of error. Alpha is the amount of error we're willing to accept. So what we hope happens is that P is less than alpha. If the p-value is less than the level of significance, then we say there's a significant result. If it's more, or for that matter, if it's equal, we say it's not significant. Again, p is less than alpha is significant. P is greater than or equal to alpha, it's not significant. Another way to think about that is to think about your calculator and the number given in the problem. If the calculator is less than what's in the problem, then yes, you do have a significant result. If the calculator is more than what's in the problem, no, you don't have a significant result. I'm going to go through an example here in just a second, but before I do, I just want to mention one quick thing on the side. When we do hypothesis tests in this class, we're going to look at what officially are called one-tail tests. And that's because when you look at the problem, it's going to tell you one side of the middle. It'll tell you whether we're looking for a result that's above or below average. And you'll know which way it's supposed to be. Another thing that, again, you might encounter if you went on and took other classes is what's called a two-tail test. In a two-tail test, the question's just going to ask you whether a result is different from what it's supposed to be, but it's not going to say higher or lower. And because of that, you could be on either of the two sides of the middle. That's why we look at two tails. Your book makes a really big deal out of two-tail tests, and you might encounter them in another class, but honestly, they're not all that important. Every problem we're going to do here will be a one-tail test and will work exactly like I told you before. And honestly, in the real world, you pretty much always have an idea ahead of time which way things are going. If I were comparing Trump and Obama's approval ratings, I've already taken the survey, so I have an idea of what the approval was for both presidents. And not just guessing, I'm looking at the results I already have. So you can look at your sample and get an idea of which way it should be for the whole population. So let's look at an example. Today we're just going to take a look at one quick kind of test. It's what's called a one proportion z-test, and it's pretty straightforward to do. I'm going to go through this problem quick, and then I'll focus in on the numbers that matter to show you how to enter things in the calculator. It says, according to the U.S. Census, just 34% of American households have children under the age of 18. A survey of 55 households in the Spencer area found that 22 of them had children under 18. And the problem says to do a 1 proportion z-test to see if the percentage of households with children in Spencer is higher than it is nationwide. We're supposed to do a 1 proportion z-test at the 5% level of significance. If you remember, the 3 steps we did were find the level of significance, find the p-value, and then compare those two numbers. Well, the level of significance is literally given in the problem, and again, it pretty much always will be. Here it said, do a 1 proportion z-test at the 5% level of significance. So 5% is our answer, and we could write that as 5%. What we're actually going to compare when we get to the last step is the decimal 0.05. To find a p-value, we need to dig out our calculator. And just like we did in the last chapter, we're going to go to Stat and then Tests. And this time, we're going to do the stuff that begins with test rather than interval. What I'm looking for this time is a 1 proportion z-test, which is choice number 5 on that list in the test menu. So you want to go to Stat, Tests, go down to number 5, and hit Enter. It's going to ask you for a bunch of information, and that information is pretty much always given to you in the problem. The important thing is just sorting out which number goes where. So when you look at this screen, the first thing it has is P0. What that is what the percent is supposed to be. It's basically saying, like, if I had the null hypothesis true, what would the percent be? And that's why it's 34% or 0.34. Then it is asking you for x and n, and you might remember we had those exact same variables when we were doing 1 proportion z intervals. This is just some number out of some number total, and here it's 22 people in Spencer out of 55 that they surveyed were people that had children under 18. The number 18 doesn't matter at all in this problem. It's just children we're looking at. So 0.34 for P0, x is 22, and n is going to be 55. When we do a p-value hypothesis test, it's really important to check and make the correct notation on the next to last line, where it says not equal, less than, greater than. What that's asking is, do we think that the actual proportion is going to be less than the P0 that we put in the problem, greater than that P0, or the not equal would be a two-tailed test where you can't really tell? You notice that on the screen here, I underlined and boldfaced the word higher. That's like the dead giveaway that we're going to select greater than. And there pretty much always will be some clue like that that tells you which thing you have to choose. If it's smaller, it's less. If it's more, it's greater. And you want to make sure that you do highlight the correct answer there. If you don't, you're going to get a completely wrong answer, and so you do need to make sure that you choose that correctly. Once you've got all your information entered, you go down to that bottom line and hit calculate, and almost instantly you're going to get a screen that looks a lot like this. And the reason it has all kinds of information on it is that there's lots of ways that you can do hypothesis tests. When we do a p-value test, really the only thing you care about on that entire screen is the line that says p equals. And here it says p equals 0.17377899998. What that's saying is that there is about a 17% chance that we would be wrong if we said this was significant. That's what the p-value is. Now, before we go on to the interpretation on this, I do want to point out it is the line that says P that's important, not the one right below that where it says P hat. What the P hat is actually saying is that 40% of the people in Spencer have kids. And yeah, that's more than the 34%, but it's not so much more that it didn't just happen by chance. Our final step is always to compare the two numbers we have. And here we have that P, which was 0.174, is bigger than alpha, that was 0.05. And remember, if P is bigger, that always means you don't have a significant result. Basically, we would be wrong 17% of the time, but we're only willing to be wrong 5%. So yeah, that's not nearly small enough. And so what we're saying is that Spencer probably has about the same percentage of households with kids as the nation as a whole. It might be higher, but really it's probably about the same. Now we're going to use basically that same process to do all kinds of different hypothesis tests, and eventually we're going to go through a lot of the rest of that menu in your test screen. But for now, we're going to get some practice with the one proportion z-tests and make sure that you know how those work. And then we'll come back and we'll talk about the different variations that you can do with it. So hopefully that'll go well for all of you and you'll be able to figure out whether or not different things are significant.